Today I will discuss briefly about the paper titled Voxel-Based Finite Element Investigation of Micromechanics Models for Stiffness Prediction of Cross-Ply Laminates and how it relates to our composite material course. Basically, composites are engineered materials made by combining two or more different substances to achieve superior mechanical or thermal properties that neither material could provide alone. The matrix binds the material together and transfers load, and while the reinforcements such as fibers or particles provide strength and stiffness. These materials are widely used in aerospace, automotive and mechanical engineering because they offer high strength to weight ratio, corrosion resistance and design flexibility. The paper focuses on carbon fiber reinforced polymer laminates, which are a perfect example of strong carbon fiber combined with a light polymer matrix can achieve high stiffness and strength, reflecting the foundation of our course. It falls under the category of polymer matrix composites with fibrous reinforcement, especially cross-ply laminates arranged in 0° and 90° layers, demonstrating how fiber orientation influences mechanical performance. The study applies the same orthotropic stress-strain relationship that we have learned using material constants such as longitudinal elastic modulus, transverse elastic modulus, in-plane shear modulus and major Poisson's ratio to form the stiffness matrix for each lamina. The paper compares the theoretical models like Voigt, Husen that we have learned in our course to predict effective stiffness from fiber and matrix properties, and then validates this prediction using a voxel-based finite element method. This method models the fiber matrix microstructure at a detailed level by dividing it into tiny 3D elements called voxel. The results show that the Husen models give the most accurate stiffness predictions, while the other models only provide upper and lower bounds. The finding aligns with our course concept that advanced micromechanical models give more realistic predictions for anisotropic materials. The authors moved to macromechanics, treating each ply as a homogeneous orthotropic layer and applying coordinate transformation to calculate properties at different ply angles. This connects directly to our lesson on how ply orientation affects global stiffness. The study then applies classical lamination theory to predict the stiffness of the entire cross-ply laminates by forming the matrices which represent extensional, coupling and bending stiffness respectively. Although the paper mainly focuses on simulation, it also relates to composite manufacturing. It highlights how accurate stiffness prediction is critical for processes like fiber placement, curing control and minimizing voids, all of which determine the quality of the final composite structure. So basically at the end, this research paper beautifully combines every topic of our course, from the introduction to the micro and macro mechanics of laminate theory and manufacturing aspects. It demonstrates how theoretical equations such as the rule of mixtures and stress, the strain laws are applied and verified using modern computational tools like finite element analysis. From this paper, I have learned that our classroom theories from the foundation and real engineering design, and that by integrating analytical models with numerical simulations, engineers can predict and optimize the performance of composite structures accurately. So, I have also prepared a report of comparing this paper and my course outlines, all the things. So, this is the report here, and I will upload this video in the YouTube and provide this YouTube link here, and thank you.